of today is to prove the spread lemma that we discussed yesterday. So I'll remind you of all of the definitions needed for that. So I mean, I'm not assuming you'll remember them. And also, this proof has some parts that are sort of not super intuitive, so I'll try to give you as much intuition as I can. So let me remind you of the relevant definitions. So we need two definitions. So one is the link. So this is a link. We saw it yesterday. So if F is a set system or a family, then the link of F at a set T is the following family. You take all the sets in the family that contain T as a subset. Contain T as a subset, and you remove it. So this was a link. And then we said that the family is spread if all the links are small. And as you make T bigger, the links get to be smaller and smaller. And concretely, we require an exponential decay. So the second important definition here is of spread. F is K spread. And I would think of K being at least 1. If the size of each link, Ft, decays exponentially with rate K. Okay, so T is any subset in the universe, not necessarily in the set system. So this was a definition of spread. And again, the way I'm thinking about spread is a sum top of a combinatorial pseudo-randomness notion. So you have a family of sets, and no element is too influential. It does not belong to too many sets. No pair of elements, no 3 elements, and so on. So no set of elements is sort of too important. So sort of it's spread around more or less evenly in a universe. And what was the spread lemma, which is our goal to prove today? So let F be a family of n sets. N sets, reminding you, it's a set of size n. Choose some parameter p between 0 and 1. And then sample W to be just a p-biased set. So from our universe, every element we include with probability p independently. So U here is a universe of all the elements. And we assume F is K spread, where K is some constant P inverse log of n over epsilon. Epsilon is another parameter, so let's put here epsilon. Then the probability, if I over W, that there is a set in my set system completely contained inside W is at least 1 minus epsilon. Okay. So this is the main lemma that we're going to prove today. This is like the main machinery that makes everything work. So why is this lemma useful? The way I see it, it is because it connects two different notions of pseudo-randomness. Our assumption is being spread. It is a combinatorial notion of pseudo-randomness. But our conclusion is a probabilistic notion of pseudo-randomness. It means that if you think of these events, that a specific set in our set system is contained in a random p set, each one of them is very unlikely, but together they are, in some sense, uncorrelated, so that with high probability, at least one of them happens. So I think of this lemma as a way of translating from a combinatorial notion of pseudo-randomness to a statistical or probabilistic notion of pseudo-randomness. This is what makes it powerful. Okay. So my goal is to prove it for you today. In fact, what I'm going to do today, I'm going to prove it with epsilon b and a half. And that already captures almost all of the ideas here. And in your problem set, you'll extend to all epsilon. So that's going to be one of your exercises today in the problem set, is to take all of the ideas that I'm going to show you today that prove this for epsilon b and a half, and see how you can modify the proof a little bit to get it to work for epsilon, for any epsilon. And it's minor changes. But I'm going to fix on epsilon b and a half today. Okay. I'm going to make one more change. So here we are choosing W to be binomial, meaning every element in the universe is selected independently with probability P. It turns out that for the proof, it makes it easier if instead we choose W to be just a random uniform set of size exactly P times the universe. So this is the comparison of G and P versus graphs of we fix the number of edges. So let me write this new lemma that we're going to prove. Then I'll show you why this new lemma directly implies this lemma, and then we're going to fix the rest of today's lecture, prove this sort of modified lemma. So let's write this of spread lemma star. So again, I'm just going to fix on epsilon b and a half from now. So again, same assumption. So F is a family of n sets, which is k spread for k being some constant p inverse log n, again, over universe U. We choose W inside U uniformly, whose size is exactly p times the size of the universe, and we get the same conclusion. Then the probability over W that there exists some set S in F, S subset W is at least a half. Okay? So it is exactly the same assumption. The only difference is our probabilistic model is not choosing W where every element is independently chosen probability P, but instead we just choose a random set of size exactly P times the universe. Okay? That's very similar. Makes it easier to prove. You'll see why later. Let me first show you why this revised spread lemma directly implies a spread lemma. So why spread lemma star implies spread lemma. Okay, so let F be a family over a universe U. Okay. And I want to apply this spread lemma star, but I'm first going to do a cheat. I'm going to view it. So let U prime be some superset of U. And I'm going to view F over U prime. So I'm going to add a bunch of elements to the universe that don't belong to any of the sets. And then I'm going to choose W prime inside U prime uniformly. So we're going to sample uniformly of size W prime being P times U prime, right? And then we can apply this spread lemma star, and we can get a conclusion. So the spread lemma star tells us that no, the probability that there exists some set in our family contained inside W prime is at least a half, right, over the choice of W prime. So our assumptions for spread lemma and spread lemma star are the same, so we can apply it if we're trying to prove spread lemma. So now we get this set W prime, giving us a conclusion. It is exactly a P fraction of this larger universe. Okay, so now final step is I'm going to set W to be this W prime intersected U. And I'm claiming the same conclusion holds if I replace W prime with W, because all of my sets are really inside the universe U. I just added these dummy elements for the reduction. So also get that the probability over W that there exists a set in my family containing W is at least a half. And then all of them claim that if I take U prime to be larger and larger, the distribution of W converges towards just sampling every element independently of probability P. So as we increase the size of U prime to infinity, then the distribution of W converges to just binomial UP. Okay? So basically, I'm saying take a universe, now increase it to a huge size, choose exactly a subset of this huge universe, W prime, of exactly a P fraction of it, and now delete all the elements you added. This distribution here is converges to just by separating every element in U independently with probability P. Okay. So yeah, so that's the end of this proof. And I mean, the whole point of it is just to justify why we can work with this model instead of the P-biased model. So the P-biased model, where we sample every element independently of probability P, is more useful in applications. But this model, where we sample it of exactly density P, turns out to be more convenient for the proof. So we're just going to stick with proving this lemma for the remainder of the lecture. Any questions so far about what we're trying to prove or about this reduction? Good. OK. So from now on, we're just going to prove this spread lemma star. So let me just erase this here. That's our goal for today. And in particular, the goal will be to see why this combinatorial notion of spreadness is useful when you're trying to prove that many events that are in some sense unrelated, in fact, are statistically unrelated. So at least one of them happens with high probability. So let me erase this part. And we're going to move on to prove this spread lemma star, again, for epsilon being a half. OK. So now I'm going to make a key definition that's going to really underlie a lot of the proof. So here is a definition of something we're going to call a minimal fragment. So again, F is a family of sets. And V is some set, arbitrary set. And we're also going to choose some set S in the family. So the minimal fragment with respect to this set system F of S and V is the following thing. I'll write it and then I'll explain. So it's S prime. Let me first just write it. S prime minus V. When you take all S prime in the family that are contained inside S union V. So what is this? I think it's best to understand this by picture. So here is V. That's some arbitrary set. And you should think of it as a large set. And here's some set S. Maybe a different color. And here's maybe a set S in our set system. Our goal will be to try to compress S. So our goal will be to try to replace S with another set in the set system, S prime, that has to be contained in S and V. But I want to push it as much as I can inside V. So I want to find a set S prime that's going to look like that. So S prime is contained inside S union V. And we're just going to care about this part here, the part that is outside V. OK? And so naturally, there could be many options how to choose this S prime, right? And we're going to choose the one that minimizes this blue arrow. So we're going to choose this. So let me use this of curly M to denote all the possible options for this. And I'll use just M, regular M, MF, SV, to choose some minimal element in this curly M, F, SV. OK, so a priori, there could be many choices how we can sort of try to compress S into V. And we're going to choose the one that's minimal. And if there are several options of the same size, we just choose one arbitrarily. Maybe, order them in some lexicographical order and choose the first one. Anything is going to work, right? Choose a one of minimal size. And typically, the family F is just going to be clear from context, so I'm just going to write this as, the minimal fragment of S and V. But you should always remember this is with respect to some set system, or some family of sets, which is usually going to be the family of sets that we're trying to analyze. Okay? So I think now I'm going to prove to you several properties of these minimal fragments. Some of them are going to be simple, and some are going to be sort of a bit more surprising. But I want to keep this picture in mind. So really, all that we're doing here is a compression type of process. So we have S and V, and we'll try to compress S into V by replacing S with another set in the set system that has the least amount of area inside S and the largest amount of area inside V. Okay? Good. So now let's prove some claims on these minimal fragments. Okay. And by the way, this notion of minimal fragments came up in the work of Hui Pham and Jin Park on the proof of the Kahn-Kalai conjecture they're going to see tomorrow. And this really makes the proof much more streamlined. So the original proof we had a different notion that made the proof more cumbersome and gave looser bounds. And once they defined this notion, everything became much slicker. So I think this is once you have the right definition, everything is better. Right? So this is the right definition here. So let's make some simple claims on minimal fragments. One, I claim that the minimal fragment of S and V is always inside S. Well, why? Because, you can see it by picture, right? We take something inside S union V, and we remove all the parts in V. So whatever is left has to be inside S. Okay? Two, MSV is disjoint from V. Again, for obvious reasons. And the last part is that somehow along the way we'll try to get in some process that you'll see later today where this minimal fragment is empty. So the minimal fragment of S and V is empty, if and only if there exists some set S prime in my family that is completely inside V. Right? Because if I can find a set S prime in my family completely inside V, I'm going to use it as S prime here. It's going to be completely inside V. After I remove V, I get nothing. And that's if and only if. And remember that our goal here is to prove that a random set contains a set in our set system. Right? That's our goal. This is what we're trying to prove. The W is some random set and contains some set in our set system. So somehow trying to push sets to be completely inside V seems to be like a good thing that we'll try to do, right? A useful thing for us. And we're going to measure how much we're able to push sets inside the random set by looking on the side of the minimal fragment that remains outside. Because that's going to be the goal. It's going to be our measure of progress. OK, so these are three simple claims. Now I want to give you one maybe slightly less simple claim. And let me erase this spread lemma because I want to keep at least this definition of minimal fragments in place. OK. So here's a slightly less obvious claim. So let F be a family, S in F, and V is subset. And let's define Z to be the union of V and the minimal fragment of S and V. So Z here is going to be this set. It's going to be, you're going to get this part from the minimal fragment and all of V, right? That's going to be the green part is going to be Z. OK. And let now F prime be all the sets S prime in our family that are completely contained inside Z. Okay? Then I'm claiming two things. One is that F prime is not empty. There's at least one such set. And second is that for all sets S prime in F prime, satisfy that if I remove V from them, I get exactly MSV. So there is a way of taking a set in F prime, removing V, and recovering the minimal fragment. And we'll see why that's important later today. And in particular, this implies that the minimal fragment SV is a subset of S prime. Okay? So again, why this is clear, why this is useful should be unclear for now. You'll see soon. First, I want to establish this. So again, what does it say? It says, take any set in the family, any other set V, take the union of V and the minimal fragment of S with respect to V, take the set system of all the sets in the family containing Z in this union, then there's at least one such set, and all sets in this family satisfy that if I remove V from them, I get exactly the minimal fragment. Okay? Yes?
In the definition of F prime, should you say S prime is a subset of Z?
Sorry, this should be S prime. Thank you. Yeah. Thanks. Yeah. Good. So let's again view the proof of that. And I do want to keep this picture here, so I'm going to erase this board. So sort of this is to be sort of traced into definitions. So let's see. So let's prove of this claim. So first of all, why is this family not empty? So how do we define MSV? MSV was defined to be S prime minus V for some S prime in F that is contained in, S union V. And we showed it to be minimal size.
Sorry, the second point here is that, so you have two lines, S prime minus V, is that an incomplete?
I said this in particular implies this.
Ah, okay.
Because if S prime minus V is this set, in particular this set is a subset of S prime. Yes? Okay. So the minimal fragment is S prime minus V for some S prime. In particular, S prime could be S. There's at least one choice here. I could take it, take the one of minimal size. So whichever S prime I chose here, this S prime belongs to F prime. Right? There's at least one such choice, by the way I define it. Okay. But now, let's see why this is true. But the whole point is that somewhere along the proof, I'm going to tell to you Z. But I won't tell you V and I won't tell you M. You just know the union. And the whole point here is that by these choices, we can recover, maybe not M, but we can recover this family F prime, because we know Z. And we can choose some set S prime there, which may or may not be the original S prime we chose here. But the whole point of this claim is that it doesn't matter. Any set here is going to contain M as a subset. And that's going to be useful. So I want to prove here the second part. So actually, let's call this S star, just so to differentiate it from S prime here. So take any S prime in F prime. So by definition, S prime is a subset of V union S, right? And so maybe it's sort of easiest to do by picture. So S prime is sort of going to be some subset of not just V union S, but V union the minimal fragment. So if it's smaller than the minimal fragment, if it's something like that, then the minimal fragment is not minimal. It could be smaller. So it's better to sort of explain it in words and write it down formally. So the proof is just by minimality. We chose this to be a minimal set. So any other set in the family that's contained in this part plus V cannot be smaller than this part. It must contain this part. Okay? So yeah, I think I explained this. If I write the proof, you read the proof of the notes. I think the proof, if you just write it down, makes less intuitive sense than just seeing it by picture. Okay? So any question on it? I mean, this is going to be a very important property. So any question why this is true? Because that's really going to make a lot of the proof work. that we can basically identify this minimal fragment as a subset of any set in F prime, and F prime is a set we can compute if somebody tells us Z. Okay, good. Okay, good. So now let's move to basically the first main probabilistic part here. Let me erase this. So let's write lemma. So let F be a family of sets, and here it's going to be convenient to think of size not exactly n, but of size at most n. Okay. And over some universe U, and let now I'm going to use a different parameter Q because we're going to reserve P for something later. So let Q be some parameter in 0, 1. And I'm going to choose V to be subset of the universe uniformly of size exactly Q U. So a subset of the universe of exactly density Q. And we assume F is K spread, where K is just some constant Q inverse. Notice there is no log n factor here. So this is a better or a weaker assumption. But the conclusion is going to be weaker. Then we're going to ask the following question. What's the probability if I sample a set in my set system F and I sample V, that's a minimal fragment of S and V is of size at least n over 2. And we're going to prove this is extremely small, 100 to the minus n, for some appropriate constant C. So what does this lemma tell us? So this is like the main engine making everything work. It says, originally, I had some set S here. And my set S might, V is going to be some small random set. S is some arbitrary set, so most likely the intersection is tiny or even empty. So S has size n. And we're going to try to compress S to be inside a random set. And we're going to do it in steps. And the main step is we're going to take a set of size n, and we're going to try to compress it inside so that whatever we have left outside has size at most n over 2. And that's going to be true for like almost all of the sets. So over a random choice of V, almost all of the sets in S are going to be compressed to size at most n over 2. And then we're going to iterate this and get n over 2, n over 4, n over 8 until we compress it down to nothing. So the main idea here is by choosing a random set, and by doing this compression operation of trying to compress the set S to be inside V, we are going to get sets where the size exponentially decrease. So after log n iterations, we're going to be done, which is why we did this log n at the end. We're going to repeat this process log n times. Okay, that's a high-level idea. So let me prove this lemma for you now. This is like the main step here. Any questions before I prove it? Yes? S is a uniform set in F. So I choose a random set in F. S is random and V is random. S is a random set in F. V is a random subset of the universe of exactly size QU, exactly density Q. Yes, both are random. Okay, good. So let's see why this is true. And now let me sort of erase this part here. So the main idea and how to prove it would be to say, well, let's say that the set S and V is bad if it violates it, if I can't compress it. And then I want to show that there are very few bad sets. And the way we're going to show that there are very few bad sets is by showing that there's a way of encoding these bad sets in a very succinct way. And there'll be very few ways of succinctly representing something, so these show that there are very few bad sets. So let's define it. So let's define the following family of bad sets. It's all these pairs of S and V, where S is something, a set in our family. V is a subset of the universe of density exactly Q. And where the minimal fragment of S and V is of size at least n over 2. And we're going to prove that this bad set is tiny, right? So in particular, this probability, the probability that M S V, again, over S in the family, and our V is more than n over 2, is exactly the size of these bad events over the number of choices I have for S and for V. How many choices do I have for sets in F? Exactly F. How many choices do I have for V, which is a subset of the universe of density QU? Well, exactly size of U chose Q size of U. Right? So this is just this probability, because we're doing everything uniformly, is exactly the number of bad events divided by the total number of choices for S and V. Right? So we just need to upper bound the number of bad events. So far, so good? Good. So now I want to encode it. So now I'm going to define an encoding argument. And again, I'll do it both by picture and by writing it down. So let me just erase this picture, because I'm going to draw it again soon. So we're going to have, so we want to encode some S and V that belongs to this bad set. So how are we going to do it? So again, let me sort of remind you the picture. So this is V, which is now a random set of density Q of the universe. We have our set S here, which originally might have no tiny intersection with V. And we're saying that we're trying to compress it to be inside V. So we're trying to choose some S prime here, also in the family. And what we care is about this area, outside V. Okay? So to compress it, I'm going to reveal information to you in steps that at the end you can use to decode S and V. So the first step I'm going to tell you is Z, which is a union of V and the minimal fragment. S and V. So it's a union of V and this red part. Yes?
This numerator over here doesn't depend on S and V, does it?
It does not. This is just a total number of S and V. Right? S is a uniform set in F, V is the uniform choice. So all the choices of S and V are in the denominator. The numerator is all the bad choices.
It's just B, though, right?
Oh, just B? Oh, sorry. My bad. You're right. Thank you. Good catch. B. Thank you. So I tell you Z. So we're going to count how many options are in a second. First, let's write it. So now, second step, I'm going to define F prime to be all the choices of S prime in F, where S prime is contained in Z. So of course, so F prime I can compute on my own. Like if I tell you Z, then you know, and the family is known, then you can compute F prime. So let me just circle all the parts that we need to actually encode. So this is the one thing we need to encode. F prime is something we can compute on our own without revealing any more information. And then we choose some S prime in F prime arbitrarily. I mean arbitrarily, but in some predetermined way. Okay, so S prime only depends on Z. Now our claim told us that the next step is that our claim told us that this minimal fragment of S and V is a subset of S prime. Doesn't matter how I choose S prime. So I'm going to encode to you. I'm going to tell you, here is this subset of S prime. So I can just give you some more information given S prime, identifying the subset M. Okay? So far now we know this part M, and we know V. So far, notice that the information I told you so far allows you to recover V and M. Why? We know the union of V and M. You know M now. So you know V. There's this joint. We put out this joint. So the last thing I want to tell you is reveal S. Now, what do we know about S? We know that S contains M as a subset. Right? Let me call this M. So the last step is going to, I'm going to tell you, S is in the link of M, right? S is a set in our family that contains M. And here's where we're going to use spreadness. We know that this link is small, so I can reveal not a lot of information and reveal S I tell you what is S inside this link, what the index of S inside this link, right? So this is how we're going to encode S and V. I'm going to first tell you the union of V in this minimal fragment. Then I'm going to tell you, I'm going to arbitrarily choose a set S prime contains an F prime. Because of our choice, M is some subset of S prime. So I'm going to give you some more information identifying M prime. We'll try to identify M. Finally, I know now that S is some set in the link of M. So I'm going to give the index of it in this link. Okay? And now we just need to do a calculation. How much information do we need to do it? How many ways that we can do it? And then that this is much less than the denominator. Okay? That's going to be the calculation we're going to do. So, yes?
For S minus M?
Oh, yeah, S minus M, you're right. This should be S. Yes, you're right. This should be S minus M within the link. But, since I know M, I can just sort of, yeah, you're right. Give you the thing. Perfect, thank you. Okay, so now let's do calculation. So how many choices do I have for Z? Well, let's even count this. Let's even condition a bit more. Let's condition on the cases where the size of the minimal fragment is M. And let's count how many bad choices we have when we fix the size of the minimal fragment. And notice that what do we know about this minimal fragment? We know that this is going to be at most n, because we have families of sets of size at most n. But also it is at least n over 2, because we only care about bad sets. Right? Bad sets are the one with the minimal fragment has size at least n over 2. We could not compress them more than that. Right? So what about 1? The number of choices of Z is what? Well, this is a set of size Q universe. This is a set of size M under this joint. So the number of choices here is exactly U choose QU plus M. Right? Because Z is exactly a set of this size. And it's not uniform, but this is all the options I could do it. And now we're going to use something very important. So here's sort of the intuition. So imagine I told you a set of size QU plus M. Think this is very big, this is very small. You don't know which parts here come from V and which parts come from M. So if I give you the union, I'm sort of hiding information. This is much less than U choose QU times U choose M. So we're using the fact that we're hiding information to make this an efficient encoding. So one thing you can prove, and again, I won't prove it now, but it's a simple calculation, is that this is at most U choose QU, the total number of choices for V, times Q to the minus M. So you lose something because of this M, but this does not depend on the size of the universe, only on the density of V inside it. So this is why we gain information by this encoding. So again, I won't prove it, but it's a simple exercise with numerical coefficients. So in particular, this U choose QU is going to cancel this U choose QU here, right? That's one thing. What about the number of choices for M? Well, I know S prime. I can deduce it from Z. So it's some arbitrary set. I know it. M is some subset of it. So the number of choices here is going to be the size of S prime choose M, right? S prime is set of size at most n, so this is now at most n choose M. And we're just going to naively bound this by 2 to the n. Okay? So that's the number of choices I have. And now, given M, how many choices do I have for S? Well, it's just the size of the link of F over a size set M. Now, we assumed F was spread, right? So it was some constant Q spread, was K spread. Let's call it K. So this is at most the size of F times K to the minus M, right? So we gain in encoding in 2 places. One place that we gain is here, where this union sort of hides which parts come from V and which parts come from the minimal fragment. And we also gain here. K minus M. This is smaller, right? So minus, what's the question?
It's M or M?
M was the size of the minimal fragment, right? We're going to then sum over all of options. So yeah, I think it's fine. Okay, good. So now let's calculate everything together. So how can we bound the size of this probability? So this is going to be at most. So let's do the numerator. So we're going to have u choose QU, Q to the minus M, 2 to the N, side of F, K to the minus M, divided by, u choose QU, F, right? So those cancel. So overall, what can we say? Let's just continue on the first board again. So overall, this probability is what? It is at most 2 to the N, Q to the minus M, K to the minus M, so KQ to the minus M, right? Good. We're almost done. Remember, we chose in this lemma K to be some large enough constant times Q inverse. C is some large enough constant, so we can say this is at most 2 to the N, C to the minus M. We also, our bad cases where M is at least N over 2, right? So we can say this is at most maybe, 4C to the minus M. And again, if we choose C to be a large enough constant, that's going to be less than like 100 to the minus M. Okay, just for a large enough constant C. So this finishes a proof of this lemma. And this is like the main lemma here. Yes? What? You have to sum over M, but you see M is from N over 2 to N. It's like exponential thing, so yeah, I agree. Yeah. No, but the important stuff here is that M is guaranteed to be at least N over 2. So all of our bounds are like exponentially small in N. So if you choose C to be a large enough constant. So that's actually important. Yeah, you had a question?
No, it was the same question.
Oh, same question, okay, good. Yeah, you sum over M, but it's the same thing, yeah, good. Okay, so this finishes the proof of this main lemma. And now to prove the full spread lemma, we just want to iterate this log n times. But before we do that, we need to do some cleanups. Okay. So let's first write a corollary of this lemma. Yes?
Is gets worse when the uniformity is smaller?
Yes. This gets worse when the uniformity is smaller. That's exactly right. Yes. So you're compressing from N to N over 2, you only lose something tiny, exponential in N. As N gets smaller, you start to lose more. And then you have to be a bit more careful. Yeah. This is exactly right. So let's do a corollary. So again, same setup. So F is a family of sets of size, at most N. We choose some parameter Q. We choose V inside U uniformly of size Q U. And we assume F is K spread for K being some large enough constant Q inverse. And now I'm just going to say that on average on V, most sets get compressed. So let's define F prime to be the following thing. The minimal fragment of S and V over all S in the family, and such that this minimal fragment is of size at most N over 2. So I'm just going to take, now this is a random set. F prime is a random family. It depends on our choice of V, right? And what I'm arguing that, let's write it here. So with probability at least 1 minus, let's say, 10 to the minus n, we have the following conditions. 1, F prime is a family of sets of size at most n over 2, but that happens always by definition. 2, the size of f prime is at least 1 minus 10 to the minus n times the size of f. And 3, f prime is k prime spread, where k prime is very close to k. So k prime is at least 1 minus 10 to the minus n times k. Okay? So basically what I'm saying is that before we analyze the probability that a random S and a random V are bad, the minimal fragment is not small enough. And now we're just saying basically this is just Markov. If I choose V randomly, then a random S is going to be good with probability 1 minus 100 to the minus n. So by Markov, with probability 1 minus 10 to the minus n, you have at least that many sets that are good. Okay? Now the third part I seem to prove to you, but I'm claiming that points 1 and 2 just follow by Markov. There's nothing. Again, you can follow the calculations on your own if you want. I mean, there's nothing deep going on here. But why? How do we get this condition about spreadness? So we had some condition about spreadness of my original family F. How can we control the spreadness of this new F prime? Yes? Yes, that's going to be a good point. F prime is also going to be a multiset. So actually, in fact, that's actually a good point. Everything I did here for sets works exactly the same for multisets. Nothing changes. So I'm not going to prove it. You can verify the proof on your own. Everything works exactly the same for the multisets. Okay? Instead of thinking about sets, think about lists of sets, not a set of sets. Everything's the same, and working with multisets makes everything much cleaner. So yeah, F prime is a multiset. That's a very good point. This is a multiset. So we are allowed to have repetitions. Very good point. Yes. So how do we prove this claim 3? So claiming claim 3 is following from the following simple claim that's going to be one of your exercises for today. So here's going to be a simple claim that you're going to prove. It's an exercise. So let F from S1 up to Sm be some multiset. Assume that is K spread. Then the following thing condition. 1, choose F prime to be any set of the form S1 prime up to Sm prime, where Si prime is some subset of Si. Just replace every set with a subset of it. Then F prime is also K spread. So this first part of this claim said, take a family of sets, replace a set with a subset. This can only improve spreadness. It never becomes worse. Again, this is just about the definition of spreadness. Just how many sets contain a specific set. If I make set smaller, it becomes harder, not easier, to contain a set. Okay? So there's this monotonicity. And the second thing is that if F prime is a subset of F of size at least 1 minus epsilon F, then F prime is 1 minus epsilon K spread. So if I delete an epsilon fraction of sets, this can only harm my spread by like 1 minus epsilon fraction. And again, this is just because sort of your side of the link can get smaller, then gets bigger, but your denominator number of sets shrinks by 1 minus epsilon. Again, both of those are like very easy calculations. It's a good way for you to like verify that you understand the definitions. So I'm not going to prove it as part of your problem sets. So given this claim, item 3 is for free. We just know it because remember that in F prime, every set here, every minimal fragment, in particular is some subset of S. So if I didn't remove anything, I would keep the spreadness the same way. Because I delete only a 10 minus n fraction of elements, I can only harm my spreadness by this 1 minus 10 to the minus n. Okay? Good. And the whole point here is this, n is going to be so large that this is never going to be change in k. Like even as n is smaller and smaller, even if you do it all the way, this can only change k by a constant factor. It's a tiny change. That's really meaningless. And also here, the side of the set system only shrinks overall, but maybe a factor of 2. Okay? Good. So now let me sort of tell you how we put everything together. So the main idea is going to be to basically apply this lemma log n times, every time shrinking things by a factor of 2. So initially, we're now going to prove of the spread lemma. So let's say initially F0 is going to be my original family of sets of size at most n. And remember, it could be a multifamily, multiset. I'm going to define F1 to be the following way. So first I'm going to maybe sample V1 in my universe of size QU. And we're going to assume that F0 is K spread for K, which is at least some constant Q inverse. And then we're going to define F1 to be basically applying this lemma. So it's going to be take the minimal fragment of S with respect to F0 of S and V1, where S is some set in F0, and such that the minimal fragment of S and V1 is of size at most n over 2. That's going to be the first step. We're just applying the lemma to the original set system. So we choose a random set of density Q from the universe, and assuming F0 is spread enough, we get and we define our set system F1 to be all of this minimal fragment that I get from V1. I try to compress into V1 as much as I can, and only keep the ones that I can compress at least by decreasing their size to at most n over 2. And basically what we've proven is that, let me not do the calculation, but with high probability, very high probability, over V1, the size of F1 is approximately the same as the size of F, and F1 is also approximately K spread. And again, if you want, you could do the calculation and see that if you go for the whole way, nothing changes by more than like a factor of 2. So that's fine. So we're good. So we show the random set of density Q, and we compress the sets of size n to size n over 2. Now we're going to do this again and again and again, log n times. So we're going to now repeat this. So now we're going to repeat this. Log n times. So I'm going to choose, we chose V1, now I'm going to choose V2 and V3 up to V log n. Each one is going to be uniform of size QU, uniform over the elements not chosen yet. So V2 is going to be uniform over all the elements in the universe not contained in V1, and V3 all the elements in the universe not contained in V1 and V2, and so on. And we're going to define this in the same way. So Fi is also going to define, as you know, take all of the minimal fragments with respect to the previous one, Fi minus 1, S, Vi, such that, S belongs to the previous family, and, all the minimal fragments, S, V, I, then we get most n over 2 to the I. So we keep shrinking them by a factor of 2 each time, and by the same calculations. So again, the size of Fi is still going to be similar to the size of F, and Fi is still going to be about K spread, and it's going to have sets of size at most n over 2 to the I. That's the important part. The size of the set shrinks by a factor of 2 each time, and nothing else changes. In particular, what are we going to get? We're going to get this. Let's look at the final state. Let's look at the stage where I equals to log n. Where I equals to log n, we're going to get that f of log n is not empty. I mean, it's a multiset, so it could have many repetitions, but it's not empty because it has size the same as f. And also, all the sets here have size 0. They're all the empty set. we shrunk by a factor of 2, and we're done. So we show that what this proves to us, and remember we said, when can we get a minimal fragment that's empty? Exactly when we can cover a set in the set system by our sets, V. Here we do it iteratively, V1, V2, V3, V log n. So what did we get here? So if I define now I'm going to set W to be V1 union V2 union V log n. So we get two things. First of all, that W is, Q log n times the universe, right? And we get that with high probability, there exists a set in my family completely contained inside W. Again, why? Because the minimal fragment with respect to W is going to be empty. We show this is an equivalent thing. So this basically finishes our proof. Only thing to note is that what did we assume? We assumed now if we're going to call this P, then now before we said K, our spreadness had to be some large constant Q inverse. Well, but now we want it with respect to the density of W, the random set that we get at the end. So this is going to be, C P inverse log n, which is what we claim to get. Yes?
When you shrink the size of the minimal fragment to a constant size,
Yes.
we don't have less steps with high probability.
Yeah, but you have a good enough probability. So the final step is going to be probably 90%. So actually, you can do the calculation and see that by the constant shows, everything succeeded probably 80%. Okay. Yeah. There is one twist to it, which is this would give you this argument if you want the success probability to be a large constant, let's say half or 90%. If you want your success probability to be 1 minus epsilon, you cannot just do this process because you're going to lose too much. You need to do a small trick on top of that, and that's one of the exercises.
You can also apply Jensen.
You can do Jensen, but there's simpler ways to get around it. You can just use this lemma, but basically, I'll sort of reveal that's the hint. So you reveal this lemma, but in the final steps, if you fail, just try again. And just try again a few more times, like log one of the times, and you allow for a few failures, and that's enough. Okay, and then you can do the calculations and see if this works. So this finishes the proof here. Okay, yes?
In the middle of the right-hand board, is there a reason that you didn't do on the second M, the subscript Fi minus 1?
No, just because I forgot. No, you are completely right. This should be the same thing as this, minimal of Fi minus 1. Thank you. Yeah. So again, the intuition here, and again, I don't have good enough intuition to explain why this works. You want to say the random set contains some set in your set system, and somehow you don't do it at once, and you don't do it slowly. You sort of do it in steps where you increase the size by a factor of 2. And I try to find variations of this where you do it in different rates, and none of them work. So again, I don't know why this works, but this works. But I think it would be very interesting to find alternative ways of analyzing this process, where either you reveal one element at a time, or you reveal them all at a time, or you do something that sort of, because I think to really understand what's going on here, we need to see more ways of analyzing this process. And other ways we have so far only analyze it when you basically shrink things by a factor of 2 at every step. Okay. So I think this is a good point to end for today. And my plan for tomorrow is to show you how we can use these ideas and modify them to give you the proof of the Kahn-Kalai conjecture. Thank you.